Okay, so I was talking about theorem 10.3 about why, if a code has a minimum distance 2n plus 1, why can I correct n or fewer errors? Well, here we have code word 1. Here we have code word 2. And it takes 2n plus 1 errors to change one code word to the other. Now, there's a dividing line here. All right, if I have less than n errors, then I'll be closer to this code word than this code word. So less than errors, I'll go this way. If I have greater than n errors, and I transmitted code word 1, then it's possible for me to decode as code word 2. Okay, but less than n errors means I'm within this, and the fact that the minimum distance is 2n plus 1 means that there's a bubble around code word 1 of radius n, such that there's no other code word that's within n of these points. Okay, so you could say that there's kind of a Hamming sphere around each code word of length n if there's a code distance of 2n plus 1. Okay. Now if you're right on the boundary here, then you know that you have n plus 1 errors, at least n plus 1 errors, but you don't know if it's from this code word or from that code word. They each could be the source of the original information. Okay, so that's kind of the upshot of the proof. You can read the formal discussion to get the complete idea. All right, now so far in our discussion of codes, we've said that the minimum distance for a code is important in determining the error detection and correction properties. But we don't have a very convenient way of measuring the minimum distance. So far, all we can do is check every single pair of code words and measure the distance between them. All right, if there's n words in your code, that means you have to choose n times n minus 1 over 2, or roughly n squared over 2 combinations. That's a lot of work. If you choose instead to have code words that have a certain structure, it becomes much more easy to analyze codes. And actually, the structure that we're going to use is based on a group structure. Okay, so here's a definition. Here's where the abstract algebra comes in. A group code is a code that's also a subgroup of Z2n. Now, what's the operation of Z2n? Z2n has operation plus. For instance, I can take 1, 0, 1 plus 0, 1, 1. Okay, this thing here is an element of Z2, 3. This is also an element of Z2, 3. Now, of course, if you're going to add two code words, they must be in the same space. So these are both in the same space. If I add these two, what I do is I add the corresponding coordinates mod 2. So I'm going to add, there's going to be 1 plus 0. The next one is going to be 0 plus 1. And then the last one is going to be 1 plus 1. And I'm adding mod 2, so that's going to be 1, 1, 0. Okay, so that's how you add two code words. You add each component mod 2. So we have a group operation. It's quite clear that there's an identity. It's perhaps not quite as clear, but there is an inverse for every code word. Okay, we have associativity because we're doing some mod 2 on each of the components, and that's associative. So we actually do have a group. We have a group structure on Z2n. Very key fact in this analysis. Now, how do you check whether a certain set of code words is a group code? How can you check that? Well, it has to be a subgroup of the entire group. Now remember, a set is a subgroup if it's closed under the group operation, and it has to also be closed under inverse. Now, one of the nice things about group codes is that every code word is its own inverse, and you can think about why that is. Try some examples and I think you'll see. So in order to have a group code, all you need to do is have a set of code words that is closed under addition. Okay, now for example, suppose we wanted to verify that this is a group code. Now what you'd have to do is actually make a Cayley table with 16 entries and show that that Cayley table is closed, that the sum of any two of these gives another one of these. Okay. All right, and they say this group is single error detecting, single error correcting. Okay, and here he says, how do you tell if it's single error detecting, single error correcting? Okay, you'd have to check the distances between any two of these code words. And that means you'd have to check 16 times 15 divided by 2, which is a lot. There's a much easier way. Looking through these code words, which code word besides 0 has the smallest number of ones? Well, the smallest number of ones, except for this code word of all zeros, is 3. Now, the key fact here is that actually the minimum weight of a non-zero code word in a group code is equal to the minimum distance. Minimum weight equals minimum distance for a group code. Key fact. Okay, that makes it much, much easier to figure out the minimum distance. And the minimum distance, of course, determines the decoding and the error detection and correction properties of the code. All right, now, this whole relation between weight and distance is introduced by this lemma. If I have two different code words, then the weight of their sum is equal to the distance between the two code words. Okay? And the way you see that is basically by looking at this example. Suppose x and y agree in the jth digit. Suppose, for instance, they're both 1. Then that digit, you take the sum, the corresponding digit in that sum will be 0. So whenever the digits of x and y agree, that adds 0 to the weight of the code word. If the two digits agree, they're both 0, again, that adds 0 to the weight of the sum code word. Okay? If the two digits differ, and I take the sum of the two digits, I'm going to get a 1. That's going to add a 1 to the weight of the sum code word. And if the two digits differ this way, also adds 1. So whenever the two digits differ, it's going to add 1 to the weight of the code word. Whenever they don't differ, it adds 0. The number of digits where they differ is exactly equal to the weight of the sum code word. Okay. Now, what's so important about this is that this sum code word, x plus y, is actually a code word in the group code. Remember, because in a group code, if x and y are code words, then x plus y must also be a code word. So if I have two code words with distance x, d of xy, there must also be a code word with weight equal to that distance, and vice versa. Okay? So that gives us the relationship between the weight, the minimum weight in a group code, and the minimum distance in a group code. Very important relationship. All right, that relationship is summarized in this theorem. Let d-min be the minimum distance for a group code. Then d-min is the minimum of all non-zero weights of all non-zero code words. Okay, he doesn't. Non-zero is kind of redundant. All the weights of the non-zero code words. Okay. All right. So here we go. All right. So now we're faced with the task of coming up with some group codes. All right. It seems hard to just try by trial and error to come up with group code. Of course, you could start with one code word and then try to generate more code words, but that actually is not going to work very well. So there's a better way to do it. All right, so we're going to use some kind of linear algebra to give us some group codes. So define the inner product of two binary n-tuples. Now, so you've seen this in linear algebra. It's called a dot product, scalar product. So what you're doing is you're doing component-wise multiplication and summing the result. Component-wise multiplication, sum the result. Okay. So if I have two column vectors of length n, and again we're doing binary column vectors, so here's one of length 6, another one of length 6, and I add them together. Oh, okay, then I get x dot y equals 0. How do you get that? Okay, let's look at that. I'm going to get 0 times 1 is 0. All right, then for the second component, it's 1 times 1 is 1. Third one is 1 times 0. So far I have 0 plus 1 plus 0, so that's 1. The next one is 0 times 1, which is 0. 0 times 0, which is 0. 1 times 1 is 1. Altogether, if you add those all up, you got a 1 from the second digit, you get 1 from the last digit, that's 2. But we're adding mod 2, so that he should say mod 2 here. Okay, so in this particular case, we have x dot y equals 0. Okay, another way you can look at this is to think of x dot y as the product of the row vector with a column vector, and here we're adding mod 2. Okay, so in example 9, we recast our parity check example in this language. Okay, so for when we encoded a 3 tuple and used a parity check bit, we added a 4th bit to obtain an even number of 1s. Okay, so what that means is every code word has an even number of 1s. That means that the sum of the digits in the code word is 0. Another way of saying that is that the digits in the code word inner product with the vector of all 1s is equal to 0. So all of our code words are characterized as exactly the set of code words such that x dot the constant code word of all 1s is going to be equal to 0. Okay, so in other words, our parity check code is a code that is obtained in this fashion as the set of code words that are orthogonal to a particular given code word. Okay, we can generalize this, and here's where we get into some more linear algebra terms. Suppose we have a m by n matrix, m rows, n columns. Here's an example. This H is in m 3 by 4 of Z2. Okay. Define the null space of a matrix to be the set of all binary n tuples such that hx equals 0. Now remember, this n is going to be the number of rows. So for instance, in this case, we have m equals 3, n equals 4. Okay. The null space of H is going to be the set of all vectors of length 1, 2, 3, sorry, that's m equals 3, n equals 5, sorry, missed that one. It's going to be the set of all length 5 vectors such that that 5 vector is orthogonal to each one of these vectors. Now, the orthogonality with each vector is going to give a different equation. The orthogonality with the first vector yields this equation. The second component plus the fourth component is equal to 0. Orthogonality with the second vector yields this equation, right? Because inner product is going to give this bit plus this bit plus this plus this bit. That corresponds to x1 plus x2 plus x3 plus x4. And the orthogonality with this vector is going to give this equation here. Okay. It turns out that the set of binary 5 tuples that satisfy this equation, we'll talk about how to find these solutions, turns out to be this. Of course, the all 0 code is always going to work, and then you can solve for the other ones. This will be a group code. It's actually going to be a group code simply by virtue of the way we've defined the set of code words. And that's actually the content of theorem 10.6. If we define a set of code words as the null space of a binary matrix, then that set of code words will be a group code. And all you need to do is prove closure under addition. It's really very straightforward proof. Okay, the proof is actually in this short paragraph. All right, a code is this. So such a kind of code is called a linear code. Okay. All right, example. Let's find the code determined by this matrix. Suppose this 7 tuple is received. So it's a simple matter to determine whether or not this is a code word. All you have to do is check whether the inner product of this matrix with this vector with this matrix is equal to 0. In this particular case, it turns out not to be a code word. We have to use decoding to find out what the correct code word is.